Let's dig into this case of the trigonal bipyramidal or TBP geometry in a little more detail. What makes the TBP geometry interesting is that it is the first and really the only geometry that has two geometrically distinct positions within the structure. The positions in the trigonal plane, the three groups in the trigonal plane, and the two groups above and below that trigonal plane. The three groups in the trigonal plane are called equatorial, and I've marked them here in blue. And the two groups above and below that plane are called axial. So equatorial here is meant to kind of evoke the equator. If you think about the Earth's equator, it runs about the middle of the planet. The axial positions are more like the North and South Pole, above and below the sort of circular plane formed by the equator. These positions are energetically and geometrically distinct. They have different bond angles, for example, with the other bonds in the structure. And so when we have lone pairs in a structure with the TBP electron pair geometry, we have this question of where to put those lone pairs. Consider a molecule like ClF3. ClF3 has two lone pairs at the central chlorine and three single bonds to fluorines. One way we could think about laying down the two lone pairs and the fluorines is to put the lone pairs in the axial positions. This seems to put those lone pairs as far apart as we can possibly get them. This does, however, create 90-degree bond angles between each lone pair and the chlorine-fluorine bonds, and these seem to be problematic. We can also think about placing the lone pairs at a 90-degree bond angle, putting one in the equatorial plane and one in an axial position. But this doesn't seem ideal because the lone pairs are now at a 90-degree bond angle, pretty much as close as we can get them in this structure. There's going to be some problematic repulsion along this red direction here. In fact, the ideal way to place the lone pairs puts both of them in the equatorial plane, both of them in equatorial positions. This leaves two fluorines at the axial positions and the remaining fluorine at that remaining equatorial position. The ClF bonds form a kind of T shape if you turn your head sideways here, and so this geometry is called the T-shaped molecular geometry. And it reflects the general rule that in the TBP electron pair geometry, we place lone pairs in the equatorial plane. They're more stable in these positions and actually experience less electron pair repulsion, electron-electron repulsion overall in those equatorial positions.